All right, in this video, we're going to look at examples that demonstrate the use of Cauchys integral formula, the first one. Of course, as we go along, even Cauchys integral formula is always going to be relevant. We got three examples here. In the first one, we're integrating this, and these are our two closed contours. In the second one, it's our integral, and that is our closed contour. The third one, which we're going to give you an opportunity to try first before you look at our answer, that is the integral. These are the three closed contours. So this is the Cauchy's first integral formula statement. So let's have a look at the first integral. So the first thing that we always want to do is to find the location find the singularities of the integrand that we have. So the singularities will be the points where the denominator of the integrand is going to be equal to 0. So for this function, the singularities are going to be, this one is going to be 0 when z is minus 2i, and then this one is going to be 0 when z is plus or minus 3. So let's just plot those ones on the Argand diagram. If this is minus 2i, then 3 is going to be somewhere there, and minus 3 is going to be there. So these are the singularities of the function that we're dealing with. Now, in the first instance, we want to integrate this around the closed contour mod z is equal to 1. So in part A, want to integrate this around mod z equals to 1. Mod z equals 1 is a circle centered at the origin, radius 1. So that circle is going to go something like this. Now, you can see that none of our singularities lie on or inside that contour. So that means this integrand is analytic everywhere inside and on that contour. So that tells us that I is going to be 0 because the integrand is analytic everywhere, is analytic on and inside C. This is by Cauchy's integral theorem, of course. Then in part B, we've got mod z plus 1 is equal to 1. Z plus 2i is equals to 1. So mod z plus 2i is equals to 1. So this one is going to be a circle centered at negative 2i with radius 1. So if we go back here, so this one is going to be centered at negative 2i, and it's going to have radius 1. So it's going to be this type of circle, and you can see that there is one singularity obviously inside, namely 2i. So what we are going to do, so that means negative 2i is our z0. Okay, so then we want from that, we want to get what f of z is going to be. So what we do is we take this to be our z minus z naught, because if z naught is negative 2i, then z minus z naught is z plus 2i, which means everything else is now going to be our f. Okay, so z naught is negative 2i, f of z is going to be z over 9 minus z squared, and then we just plug into the right hand side of this formula here. So that means the integrand going to be 2 pi I f of z naught. So we're going to plug in this there. So this is going to be 2 pi I. If I plug in negative 2i there, the numerator is going to be negative 2i, the denominator is going to be 9 minus negative 2i squared. 2 pi I, this is going to be 9 minus, I think this is going to be negative 4. Okay, so it's going to be 2 pi I negative 2i over 13. The i's are going to so this is going to be 4 pi over 13. So that's going to be the value of that integral along that contour. Okay, so that sorts out number 1b. We're now going to go to number 2. In number 2, we have the integral of e to the z over 4 dz all divided by z squared plus pi squared. Again, the first thing we need to identify the singularities of this function. This function is going to be singular when the denominator is 0, so z squared plus pi squared is equals to 0. Z squared is minus pi squared, so z is going to be plus or minus pi I. So if we plot these, we are going to have pi I here, negative pi I there. So those are the singularities. Now let's look at the contour. The contour we're given 1 plus or minus 4i minus 1 plus or minus 4i. So so if this is 1 here, 1 plus 4i, so the question is 4i bigger or smaller than pi I? Pi is 3.14, so 4i is going to be bigger, so that's going to be just there, and the other one is going to be just there, and then negative 1. So this is what our contour is going to look like. So that is our contour. And both of the singularities are inside. Okay, so that's presenting us with a slight problem, because the Cauchys integral formula only caters for the case where we got only one singularity inside. However, we are going to use techniques from first year to sort this out, what we're going to do is we are going to write this as e to the z over 4 times 1 over z squared plus pi squared. This we can write as e to the z over 4 times 1 over z plus pi I into z minus pi I. And then we are going to resolve these into partial fractions. Okay, so we're going to write this as a over z plus pi I z plus pi I plus b over z minus pi I, and then look for a and b. Okay, I am not going to do that because we can't do that. It's a first year's skill. We are going to find that this works out if we have got 1 here minus 1 here, and then all this is multiplied by 1 over 2 pi I. So what it means is that a is 1 over 2 pi I, b is negative 1 over 2 pi I. Okay, just make sure you can do that. So therefore the integrand now, so back to this, if we can rewrite, so the integrand we can rewrite as e to the z over 4 divided by 2 pi I 1 over z plus pi I minus 1 over z minus pi I. Okay, then we're going to use the property of integrals, the fact that the integral is a linear operator, and write these two, write this integral as two integrals, 1 over 2 pi I. In the first instance, we're going to have e to the z over 4 dz divided by z plus pi I. And then in the second instance, integral e to the z over 4 dz divided by z minus pi I. Now this integral has got only one singularity, and that integral has got only one singularity, so we can apply Cauchys integral formula here and here, and we don't have that problem that we had before, where this integral had two singularities inside our contour. So for the first one, so z naught is going to be negative pi I, and f is just going to be this. With this one, z naught is going to be pi I, and f is going to be that function. So that means we're going to have 2 pi I times 2 pi I. This 2 pi I now is coming from Cauchys integral formula, because it has got 2 pi I there. Then f of z naught, we said for the first integral, z naught is negative pi I. So it's going to be e to the negative pi I over 4. If we substitute, then minus, this one is going to be e to the pi I over 4 times 2 pi I again, sorry. times 2 pi I. And then if we factor out the 2 pi i's, going to cancel out with this 2 pi I here. So this is going to be e to the minus I pi over 4 minus e to the pi I over 4. This is just the reverse of what things should be like if we had sine pi over 4. Okay, so we're going to do that. So if we reverse them, pi I over 4 minus negative pi I over 4, we need a 2i there, so we plug in 2i there. That means it's going to be 2i outside. So this is going to be equal to 2i sine pi over 4. This is 2i. Well, sine pi over 4 is root 2 over 2. So this is going to be I root 2 is going to be the value of that integral there. Okay, so we're now going to give you an opportunity to have a go at number 3. Where is number 3? There is number 3. So just have a go at the number 3. You can pause the video, and then when you continue with the video, you can compare with our solution. Right, so what we have in number 3 is this integral here. The singularities are the points where the denominator is 0, because this is an entire function, that's an entire function. So this is 0 when z is 5 or minus 5. So these are the two singularities. For A, we are looking at the contour, which is a circle centered at the origin, radius 2. Gonna look something like this. There are no singularities inside or on this contour, so that tells us straight away that I is going to be equal to 0 by Cauchys integral theorem. Then in the second case, we got z minus 4 equals to 2. So this is a circle centered at 4 with radius 2. Okay, so it's going to look something like that. So this one is definitely going to be encircling the singularity at 5. So if we write our integrand like this, then this is going to be our z minus z naught, because our 5 is our singularity. So that means this is going to be f of z, as I have written here. So the integral is simply going to be 2 pi I f of z naught. Z naught is 5. So we just need to plug in 5 into this thing here and multiply it by 2 pi I. So it's going to be 2 pi I 5 cosine 5 pi divided by 5 plus 5. Cosine 5 pi is negative 1. 5 over 5 plus 5 is 1 over 2. So it's going to be 2 pi over 2 times negative 1. Going to be minus pi I. Okay. Then for part C, we have got mod z is equals to 6. So that's a circle centered at the origin with radius 6. Okay, So this time our contour is including both singularities, but we've already seen in number 2 that we can deal with this using Cauchys' first integral formula by decomposing this into partial fractions, and you shall find it works out to 1 over 10 into 1 over z plus z minus 5 minus 1 over z plus 5. Okay, therefore our integral we can write as the integral of z cosine pi z divided by z minus 5 dz minus integral of z cosine pi z plus 5 here. This is all times 1 over 10. This has got only one singularity, and it's z equals to 5, so z naught is 5 here. This is going to be our f. Here z naught is negative 5. It's going to be our f. So this is how this is going to work out. So there is going to be 2 pi I over 10, this 10 here, times f of z naught here is going to be 5, plug in 5 here, and plug in 5 there. Take away 2 pi I over 10, then we're going to have negative 5 cosine negative 5 pi, and that's it. So let's see how this works out. It may not give us 0. This and this gives us pi I. Cosine 5 pi I is negative 1, then minus it's actually going to be plus, minus and minus there, so it's again going to be pi I. Cosine negative 5 pi is the same as cosine 5 pi, so it's going to give us minus 2 pi I. Okay.